Hello and welcome to this episode of Math with Martinez. We are in our Pre-Cal Unit 10 entitled Vectors. And this episode is all about bearings and direction. So let's go ahead and begin. The direction of a vector can also be given as what is called a bearing. And bearings are frequently given in application problems. So let's go ahead and look at how those ideas of a bearing and a vector are connected to one another. A quadrant bearing is the acute angle between a vector and a north-south line, or our y-axis, which you can see here in this diagram. The bearing here would be to the right 60 degrees in the eastward direction from the south axis on your compass, and that would be written as S 60 degrees east, like you see here. So you kind of want to write your bearing as you would give your directions. So it's from the south, go 60 degrees east. Doesn't that make sense when you kind of think about it like that? So from the south, so from S, move from here, from south, move 60 degrees in that eastward direction. That tells you how to write it in the bearing form. True bearings are the angles measured clockwise from the north to the vector. The true bearing of a vector to the right is 120 degrees. True bearings are written with 3 digits, so if your true bearing was 15 degrees, it would be written as 0, 1, 5. You're going to use 3 digits, and so you may have a 0 in front as kind of like a placeholder. So let's go ahead and look at a few examples here together. We're going to begin by identifying the quadrant bearing for each, and then the true bearing from each. So let's begin. Our quadrant bearing, remember, that is written telling us from either north or south how many degrees we're going to go, either east or west. So in this example, we've got it marked that our vector has rotated 85 degrees from the x-axis. So if you were to think about this more carefully, remember that we have our north, south, east, and west. And so we are going to be measuring from north. So my quadrant bearing is going to be from north. How many degrees am I going to have to move? I'm going to have to move over this amount, which how much would that be? Well, it's just the remaining amount to go. If right here was 85, then all that's left is 5 degrees. So you'd be moving 5 degrees. That's that little piece that's missing, and it's going to be in the eastward direction. So there you go. Now what would be our true bearing? Your true bearing is always measured. Let me highlight this. It's the angle measured clockwise from the north to the vector. So from north, from our north axis to our vector, what's that going to be? Well, it's actually just the same amount. It's going to be 5 degrees from north that we're rotating. And so we would say that. Also clockwise. Clockwise means going in the direction that the arms of a clock would go. So I just go 5 degrees, but I'm going to write this with 3 digits. So 0, 0, 5. Okay, let's look at example 2. What is going to be our quadrant bearing here? Well, we're going to be measuring from our vertical axis, so either from north or south. Which one is it closer to? Well, it's closer to my south axis. I'll be able to create an acute angle if I go from my south in that westward direction. Now, how many degrees is that going to be? Well, let's see if we can figure this out. this portion right here is 212, and this is the portion I'm looking for. Well, together, how many do those give us? What is that together? The two little angles that I've marked, that would be 270 degrees. So if I just subtract my 212 from that, it will give me that leftover portion that we're looking for, and that is 58 degrees. So from south, I'm going to go 58 degrees to the west. There we go. Now, if we're going to figure out our true bearing, it's from north, rotating clockwise, so in the direction that a clock goes, which would mean I'd be going all this way around. So how much is that? Well, I go 180 degrees and 58 more, because that's what this portion is right here. This little portion is 58, right? We found that just above. And 180, so if I take 180, add to it 58, then that's going to give me 238 degrees. And that is 3 digits, so I don't need to add any like zeros in there to start it off with. Okay, now, third example, the quadrant bearing. Do you guys want to go ahead and try that? What would be the correct way to write to give our quadrant bearing for this angle? So we'd be measuring from north, this acute angle, and that angle is actually already given to us. We know that amount is 24 degrees. So from north, this is north, we're going to move to the west 24 degrees. Now, what about our true bearing? Can you guys figure out what that true bearing would be? So I'm measuring from north. I've got to go clockwise and terminate at that vector. And so those two parts together, right? The two parts together are 360. I'm just trying to figure out, okay, if I take away the 24, this little amount in here, if I subtract that from 360, that's going to be that angle that I've marked in purple. And that is 336 degrees. And that is 3 digits. So we're good. We've got it in the correct format. Okay, so that was just looking at some diagrams. Now let's look at some application problems. An airplane is flying at a bearing of 245 degrees at 550 miles per hour. We're going to give the velocity of our airplane as a vector in component form. All right, so when in doubt, let's draw it out. So here is our little coordinate plane, and we are flying at a bearing of 245 degrees. So from that north, I need to go 245 degrees. That means I'm going to be terminating here. Right there. There we go. And we have that this airplane is going 550 miles per hour. And so what we're going to do is give our velocity of our airplane as a vector in component form. So to do so, what we will have is we're taking our magnitude. What is the magnitude? Our magnitude is 550, and our vector in component form is going to be our trig ratios, which is cosine of our angle, which would be 200, which would be the difference of our 550 miles per hour, and I'm sorry, the 245, and really I'm looking for it in standard form. So look here, let me show you on this side right here. That is 245, but if I'm thinking about this like I would my unit circle, then I'm measuring to here. So how much is that going to be? Think about this with me. How much is right here? What would this amount be? That amount is going to be 245 minus the half rotation, which is 180. Grab your calculator real quick with me. So this part right here is 65, which means that right here, let me switch colors a bit. Right here, 90 minus your 65 is 25. And add to that your 180, and that means that this angle here in standard form is 205 degrees. So we have cosine of 205 degrees and sine of 205 degrees. Now again, why is it that I'm writing it like this in taking my miles per hour and multiplying it with sine and cosine? Well, think back with me here like we did previously. Trig forms of any vector are just the product of their magnitude and the unit vector u. And the unit vector u is just your, right here, cosine theta, sine theta. So that's what we're seeing here. We're writing it in that component form by taking the product of its magnitude, which is its miles per hour, and the cosine and sine trig functions. So what's this going to be? When we write this in component form, it would be 550 cosine (205) and 550 sine (205). We can grab our handy dandy calculators to evaluate that. Make sure that your mode is correct, that we are in degrees. Good. And that would be negative 498.47 and negative 232.44. There you go. Let's do another one. We've got a man that's pushing a lawnmower with a force of 25 pounds uphill at an angle of 40 degrees. Okay, so let's kind of sketch this out. So this is a force application problem. And he's pushing this lawnmower uphill. And that is 40 degrees. So he's going uphill at 40 degrees with a force of 25 pounds at that angle. So what we're going to do is give the force exerted on the mower as a vector in component form. Okay, so how do we write that? Remember that to write a vector, it's just going to be its magnitude times our unit vector. So what are those values in this specific instance? It's going to be the magnitude, which is 25, being multiplied with cosine of our angle, which is going to be 40 degrees because it is, we're thinking about it like we would our unit circle. How many degrees have we rotated? And sine 40 degrees. All right, so we're going to be taking 25 times the product of 25 and cosine 40, and the product of 25 sine 40 degrees. And then you just go ahead and grab your calculator and find that product. So that would be 1915 and oops. Sorry, my key didn't click. There we go. That is the component form of the force that is exerted on this lawnmower. All right, now just one more that we're going to do, and that is a boat. A cruise ship is sailing at 20 knots in the direction of north, 12 degrees west. Again, so we've got a cruise ship and it's sailing at 20 knots in the direction 12 degrees west of north. We're going to give the velocity of the cruise ship as a linear combination now of our unit vectors I and j. So not just in component form, but as the linear combination of our unit vectors I and j. So to begin, when in doubt, draw it out. And it's sailing 12 degrees west of north, so that's going to be right here. And this amount of rotation is 12 degrees. We're 12 degrees in the westward direction from north. Okay, and we're going to go ahead and figure this out by applying our understanding that our vector is going to be the magnitude times our unit vector, and that would be our magnitude of 20 multiplying with now sine and cosine, but we need to figure out how many degrees that is that we have rotated. We've gone 12 degrees west of north, but what we want to do is figure out just how much we've gone if we're thinking about it in standard form. So how much would that be? Well, it would be 90 plus our 12, which is 102 degrees. So that's what we're going to want to plug in here. It's cosine of 102 degrees, and also our sine of that amount, 102 degrees. Okay, so now let's go ahead and begin to simplify here a bit more. It's going to be 20 cosine 102 degrees, 20 sine 102 degrees. Let's get that product. Grab your graphing calculator. That is negative 4.16 and positive 19.56. But what we want to do is write this as the linear combination of the vectors I and j, and so that would be to write it as negative 4.16 times vector I, and add to that 1956 times vector j. All right, there you have it, ladies and gentlemen. That is taking bearings and direction and seeing how vectors are going to be so critical in this application kind of scenario. So if you guys had any questions, would you please take a moment and share those now? And until next time, stay fired up.